Right. Now everything is good now. So now I am mentioning that as I'm mentioning, so that what I'm mentioning that if A is one operation is applied, I get a new matrix. These two matrices are not said to be same, but they are similar. So they are not same, they are said to be similar. In what context they are similar? They convey the same sort of information. Conveys the similar information. Similar information. What is the meaning of similar information? Let me speak out about this. Similar information. So what is the meaning of that one? Let me take up, I have x plus 2y is equal to 3 and 2x plus 5y is equal to 15. Let us say I have equations. Two equations, two unknowns. Let me write 1, 2, 2, 5 into x into y is equal to 3 and 15. 3 and 15. So the augmented matrix, if I am writing, this is called the concept of augmented matrix. We are writing it as 1, 2, 2, 5, 3, 15. So this is called A colon B. We call it as an augmented matrix. Augmented matrix. So which combines the right hand side matrix with the coefficient matrix. We call this in the form of Ax is equal to B. X is called a solution vector. P is called RHS matrix or RHS vector. And this is called the coefficient matrix. Coefficient matrix. So the coefficient matrix is added with the RHS, then this is called the augmented matrix. Now here what I am doing now, I am doing a sort of R1 changes to R2. So I written as R12. What is the meaning of this one? 2, 5, 15, 1, 2, 3. So from this augmented matrix, rewrite the system. What happens? This becomes 2x plus 5y is equal to 15 and x plus 2y is equal to 3. Now is there any change in the system? Is the system is changed? Change in the system? No. There is no change in the system. The system is same. So what it conveying is same conveyed by the system. What the solution this has? The same solution it has. What is the change? They are not same. I am not saying they are not same. They are similar. They are similar. Because here this is my first equation, this is my second equation. But here this is my first equation, this is my second equation. My equation's order is changed. So that's why they are not same, but they are similar. So the context of similar is clear. They convey the similar information. So that is why we are talking about these elementary operations will play a very important role when you are talking about the system of linear equations. We are going to apply this row operations. We'll be converting into a beautiful structure. We call it as echelon form. Echelon form. Okay. We call it as a echelon form. So what is an echelon form? Echelon form is having a standard form. It is having a standard form. So what is a standard form? We'll be talking about, there are two types of row echelon form or column echelon form. Column echelon form. I write it as row or oblique column echelon form. Row or column echelon form. Okay. Sir, once show the previous slide. So is it clear? Yes. Now let me continue. So the way in which we are defining this beautiful form is for any matrix A. So it is independent on the order. The order can be anything. Because sometimes you can have two equations, three unknowns. Sometimes you can have 4 equations in 2 unknowns. Okay, so that's called a matrix is said to be in row echelon form. It is said to be in row echelon form. Row echelon form. If the first condition, any 0 rows are existing, any 0 rows are existing, they must appear. They must appear at the bottom. Something like if there are any stones in the water bowl, they will be appearing in the bottom, right? So all 0 rows should happen at the bottom. So this is how we are mentioning. If there are any 0 rows, what is a 0 row? All entries in the rows are zeros. So they should be at the bottom of the thing. The second point. The number of zeros before the first non-zero entry. Before the first non-zero entry, the number of zeros, I repeat, the number of zeros before the first non-zero entry. So what in by first non-zero entry? The non-zero entry in the sense I am considering this is a row. So first element is 0, second element is 0, the third element is 2. So this is my first non-zero entry. After that there may be a 0, there may be a 0, there may be a 1. But this is my first non-zero entry in a row. So the number of zeros before the first non-zero entry, a row by row should be strictly increasing. So should be strictly increasing. What is the strictly increasing? It's called monotonically increasing. Means, for example, there is a 0, there is a 0, there is a 3, let us say. There is a 3. Followed by 0, 2 or something like that. Why should I bother all the zeros? So this is 5 and 4, like that it is having. So what are the number of zeros before the first is non-zero entry? There are 2 zeros before the first non-zero entry. Here is also 2 non-zero rows are available before the first non-zero entry. Now once I fix it, so that is called the number of zeros are 2, the number of zeros are 2. So it is not strictly increasing. What should I do? Making use of this one, the below entries are tending to 0. So what should I do? That is called, I can make one operation, 3 times of R. This is, let us say, ith row. Ri minus 2 times of R, let us say, this is I, this is J. So Rj is within Ri. So once I apply this operator, the below elements will be making 0. So like that I can make, should be in increasing. Okay, there is an optional point to be remembered. It is called, I am saying it's an optional. That's called every first non-zero entry is 1. Unity. So this is optional. Why I am treating as an optional? Suppose this is 3 now. It is the first non-zero entry. So this is not unity. What should I do? Just I'll take I divided by 3 after Lagrange stages. Now it becomes 1. But this will make some fractional over the rest of the elements. So that's why this last step I can take later at the last case. So this is how we are talking about the row echelon form. So it should be in increasing. So it should be 0, 5, 0, 0. So now this is increasing. Number of zeros are 1. Number of zeros are 2. Now I can make this 0. Number of zeros will be 3. So it is the number of zeros before the first non-zero entry will be increasing. Okay. I can make a more clarity of this one. I can make a little bit. So Z1, Z2, Z3 or the number of zeros before first non-zero entry in R1, R2, R3 and so on and so forth. So these are the number of the Z1, Z2, Z3 stands for the number of zeros in the first row, second row, third row, like that. Then we should have, or we must have that Z1 is less than, Z2 less than, Z3 less than, so on and so forth. But after reaching some zeros now, how many number of zeros are there? There is no any non-zero entry, so there is no question of that one. These are all zeros, so the block is called 0. Sorry. So this is how we are making. And this is first non-zero, this is before the non-zero entry. If all are zeros, there is no question of this value with respect to that particular row. So this is clear? Right. Now, so you can write. So, a beautiful concept we are defining as, a beautiful concept makings of this is defined as is a rank. So what is the rank? What is the rank? Rank of A. So if A is given M cross N matrix, now here it can be of any order. It can be of any order. If M cross N, then the rank of A is equal to said to be R if and only if there exist R number of non-zero rows in a row echelon form, which is similar to the column echelon form. Column echelon form. Okay, this is one way of giving the things. I can also quote the rank using the minor. So this can be written as it is the order of highest possible minor. Highest possible non-zero minor. What is the meaning of non-zero minor? What is the meaning of this one? It is the order of a highest possible non-zero minor. If the rank is R, let us say if the rank is R of a matrix A, then the minor of order R plus 1 cross R plus 1. So I am talking about any order more than that R. Its minor will be 0. Every minor of order more than R will be 0. And at least one minor of order R will be a non-zero. So, and at least one minor of order R cross R. At least one minor of order R cross R is non-zero. So this is at least. But this is all. So all orders of minus more than R are becoming 0. So this is the way in which we can define the rank. So for that you can write the practice problem 4. I think P3 is completed, right? Previously, let me check it. Otherwise numbering will be missing. Yes, P1, P2, P3. Now this is my P4. P4 is find the rank find the rank capital A 1 2 3 0 1 2 3 0 2 4 3 2 3 2 1 3 6 8 7 5. Find the rank by reducing to row echelon form. By reducing into row echelon form. By reducing into row echelon form. Okay, then P5. Based upon the time, you can work it. They're all not compulsory to submit. Okay, there is no submission for these problems. According to your time and convenient, you can practice these problems. If some sign is mistaken, you will get another problem. That is nothing wrong. -1 1 0 1. Suppose instead of -3 you written +3, you will get some other problem. Okay, but process is simple. So find the rank. So all these problems comes under the find the rank. Find the rank by row echelon form. Okay. You need one more, P7. Because these conversions are very important, you will be using this. But generally we will be using 3 by 3. But for the sake of practice, I am giving this. 3 5 4 2 1 3 and 8 4 7 13. And few of these problems we might have worked out at class. In the class while we are discussing, you can practice it. P8 4 4 -3 1 1 1 -1 0 K 2 2 2 9 9 K 3. So find K such that it does not show that this is such that the rank of A is 3. If the rank is going to be 3, then what is the K value? Okay, you just try it. We can take submatrix. Yeah, actually when you are proceeding for, you need to evaluate the determinant, 4 by 4 determinant. If it is 0, go for 3 by 3 determinant. So that is how we are evaluating. When I'm talking about the highest order minor, the process for this case, go on, apply row operations such that this will arrive. But when I'm coming to the case of the rank by minor, now I need to take up, if A is given 5 cross 5 matrix, step 1 says if you evaluate this 5 cross 5 determinant, if it is 0, then check all 4 cross 4 matrices. How many are there? There are 5 different 4 by 4 minors. So all 5. If all are zeros, if all are zeros, if at least one is not 0, declare that the rank is 4. If it is not equal to 0, declare that the rank is 5. So if go to step 2. If it is not 0, stop and declare rank is 5. If it is not 0, declare rank is 5. If it is 0, then go to this one. If all the are zeros, then go to step 3. So this is my step 2. If at least one is non-zero, means if at least one is non-zero, then declare that the rank is 4. So when all are zeros, go to step 2, step 3. What is step 3? Identify all 3 by 3 minus. How many 3 by 3 minus are there? 5C3 into 5C3, 5 into 4 by 1 into 5C3. 5C3 is equal to 5C2. 5 into 4 by 1 into 2 in the sense 10. 10 into 10, 100. There are 100 3 by 3 matrices. If all are zeros, then go to step 4. Step 4. Step 4 talking about all 3 by 3 or 2 by 2 matrices. How many 2 by 2 matrices? 5C2 into 5C2. So how that 5C2 coming? I think I explained that. You can think of it. If it is not at least not 0, at least one is not 0, then declare that the rank of A is 3. So like that I need to proceed until the order of 1 comes. Yeah, you need not to copy. I will share this. Okay, anyway, you can copy. Okay, so these are the problems. So P9 is 1, 2, 3, 1, 2, 3, 2K7, 2K7, and 3, 6, 10. Find K such that the rank of A is 2. Such that the rank of A is 2. Yes, it is visible. Okay? Yes, okay? So this is the P9. And don't be afraid that I am going on adding the problems. Only the thing is that I mentioned my concentration is on the concept. First method to form upper triangular matrix. Yes. The way in which we are proceeding for row echelon form, it is resulting into upper triangular matrix. But it is not all the time, because sometimes anyway the principal diagonal elements, the number of zeros will be increasing in the upper triangular matrix. So upper triangular matrix is an example for the row echelon form. Is an example for the row echelon form. Now let me go further. So like that you can work out many. If you want, I can give 10 more problems on the same idea, but okay, let me not. The next concept is reducing into normal form. Normal form. So the previous one is a row echelon form. Now this is a normal form. So a matrix A, which is of order m cross n matrix, can be converted into a normal form, by applying the row sometimes or row and column operations. When I am talking about this row operations, I can apply only row operations to convert into the echelon form. But sometimes, because based upon the order, I need to apply the column operations also. If it is beautifully as a n cross n matrix, I can apply only row operations. Then I can convert to the normal form. If the number of columns are more than the number of rows, then I need to take the help of column operations. Okay? Sometimes. If the number of rows are more or columns are less. Okay? So that depends. For example, I am talking about, so what is the normal form? So the normal form is having a special structure of IR. This is 0, this is 0, this is 0. So 0 in the sense, this is R cross R matrix, which is of identity. If my matrix is of n cross m cross n matrix. So already r rows gone. Then how many rows will be lefting? So there will be m rows na. So it will be m minus r rows cross r. This is mine. So it is called, I call it as O3. I call it as O3. The O1 will be of order. There are r number of rows. How many columns left? There are r columns are there here. Then there are n columns. So it will be n minus r columns. So this will be n minus 1 columns. Now this is my, this is 2, this is 2. Only for the sake of numbering I am giving it. This O3 will be of order R. This would be m minus r cross n minus r. So I repeat, the I is a r cross r order. The O1 is a r cross n minus r order. O2 is a m minus r cross r order. And O3 is a m minus r cross n minus r order. So this is how, by applying the row transformations and the row and column operations, I can convert this given matrix A into this standard form. We call it as, yeah, that way, sir, which is better? Is it row operation or column operations? Based upon, preferably try to go on apply the row operations. And again, if you are not able to make this sum of the elements to be zeros, or some of the elements are not in the identity formation, because if the rank of A is R, then we can convert, or we can make the A is similar to the IR 0, 0, 0. If it is not of a rank R, because every matrix will have a rank. What is the rank of a matrix? It can be anything from 1 to the highest order. So always, if A is a rank, A is of order m cross n, the rank of A is always less than or equal to the minimum of m comma n. So that is one beautiful property we should make. The rank of A is 0. This is possible only if and only if A is a null matrix. A is a null matrix. It's called null. It's called a null matrix or zero matrix. The other way, the rank will be at least 1. The rank will be at least 1. So I can say the rank of A is always lies between. So if A is a non-zero matrix, if it's a non-zero matrix, then 1 less than or equal to. So it must be either between 1 to the minimum of those things. Okay. So based upon that rank, I can construct this normal form. Okay. So one way is that I can apply the A operation. So A is similar to the IR 0, 0, 0. So in between I am going to apply the operations. I can apply operation 1, operation 2, operation 3, like that. Some number of operations. These operations can be either maybe a row or a column. So preferably I'll apply the row operations until I could be able to proceed. Then after I'll apply the column operations. But few people will be doing this one. So using this one, using this A11, make all the below elements to be zeros. So for that I need row operations. Row operations. How many row operations? If my order is a m cross n matrix, so I need these many operations, m minus 1 row operations. And again in the next step, after they are converted into 0, 0, 0, then I'll use this one, use the column operations, How many are there? There are n columns. So 1 is already left. So use n minus 1 column operations to make them to 0. Now this is equivalent to A11, 0, 0, zeros, all zeros, here all 0, 0, all zeros. Then make use of A22, make these zeros, make these zeros. So this is how few people will be working, row followed by column, row followed by column. But few people will be, so this is one way of this is one way of applying the row by column. Row, column, row, column, they proceed. The few people will be working with, I use the A11, make the below elements to zeros. I use the A22, above and below will be zeros. This is possible. Makings of A33, I can make above and below to be zeros. But as and when a situation comes where still extra rows or extra columns are left with us, then I'll be using the column operations. Thus, there the column operation will come into picture. So for example, I have 3 rows. I have 4 columns or 5 columns. So using this one, I can make the zeros. Using this one, I can make the 0. Using this one, I can make about 2 elements. Now still I need to make them zeros. So then how can I make now? I can use the column operations. I can use the column operations to make this 0. I can use this column operation to make this 0. I can use the column operation to, so like that I can, some column operations, that depends upon the number of columns left. So this is the idea. This is the idea. Now you can take I think, what is my count? P9 is the last problem, right? P9. Now let me go with the P10. So P10 is capital A is equal to 1210 1210 minus 2430 102 minus 8. Find or convert to reduce to normal form. So this normal form is also, we call it as canonical form. Normal form are as well as canonical form. Both are same. P11. So I need to apply the row operations. Make use of this one, make these 2 zeros. Make use of this one, make above and below are zeros. Make use of this one, above are zeros. Now how to make this 0? I use this C3 to make it 0. That's how it comes. Let it be. So you think of it. My P11 is 0, 1, 2, minus 2, 4, 0, 2, 6, 2, 1, 3, 1. Now please that in this problem, if I am making this to make this 0, it is not possible, because from 0 I cannot generate anything, right? 0 into anything is 0. So first issue I need to take, first interchange R1 to R2. Then I change. Otherwise R1 is interchanged with R3. Use anything, make the non-zero entry there, then go on apply the process. Okay, that is a hint. Now P12 1, 2, 3, 0, 2, 4, 3, 2, 3, 2, 1, 3, 6, 8, 7, 5. Okay. P13 143 minus 2 1 minus 2 minus 3 minus 1 4 3 minus 1 6 7 2 9. Just for the practice I'm increasing the order, that's all. Minus 3 3 6 6 12. You see that after reducing the canonical form, I can also find the rank. find the rank. What is the rank? The order of the identity matrix that is appearing in the normal form is the rank. Okay. So also find the rank for these problems. You need one more? I think it's enough. Okay. So let me do this. P14. So this problem can help us to build up our next topic. 1, 2, minus 1, 3. 4, 1, 2, 1. 3, minus 1, 1, 2. 1, 2, 0, K. Find K such that the rank of A is 3. Actually, the order is 4 by 4 na. Now I need to get the rank is 3 so that what could be the K value. Okay. That's good. Fine. So like that I can make many problems there, but okay, as per the concept is clear, that's enough. Okay. K is 0. You check it. You have to evaluate. Next, a concept of elementary matrix. So I spoke about this one. It's saying that it says that it is a matrix obtained from the identity matrix I by a single either row or column. I call it as either row or column. Single row operations. So on the identity matrix, you apply only one operation. The resulting one is called the elementary matrix. For example, this is the identity matrix I have. This is the I3. So I3 I have. I am applying one operation called R2 and R3 are interchanged. What I can get it now? 1 0 0 0 0 1 0 1 0. Now I say that this is one elementary matrix. This is one elementary matrix. What is the other? I can apply the one operation. So only single operation, please remember. On this one, if I apply one more, that is not considered as an elementary. So I am applying 2 times of R2. So this becomes 1 0 0 0 2 0 0 0 1. This is one elementary transmission. This is one elementary matrix. I am applying one operation. Only one operation. Any one operations. I am writing R2 is equal to 3 times of R1 plus R2 is equal to R2 plus 3 times of R1. Please check it. This will be resulting into an elementary. So it is only R2 is changing. R1 is 1 0 0. R3 is 0 0 1. What is R2? 3 times of R1 is added. So this becomes 3 times of this R1 is added. So this is another elementary transmission. This is clear? So you apply on the identity matrix, you apply any one elementary operation. The resulting one is called the elementary matrix. Okay. Understood, huh? So after this we have moved on. Yes, yes. Now it's visible? Yes, yes. Okay. Sir, we can get infinite. Explain a problem on Gauss. Okay, Gauss elimination. I'll try. So yes, there are infinitely many elementary matrices. Because you multiply with I multiply with the 2. You may multiply with the -1. This is another elementary. So there are infinitely many elementary matrices because I can generate infinitely many operations. But you apply any one of them, I'll get a elementary matrix. Okay. Then later on we have moved on to a system of system of linear equations. System of linear equations. So what is a system of linear equations? There are n number of equations in m unknowns or m equations in n unknowns, whatever it is. So we can think of first equation is a11 x1 plus a12 x2 plus a13 x3 plus and so on and so forth a1n xn. So this is equal to b1. Second equation is a2. I'm talking about the second equation, so it starts with 2. 1 x1 plus a22 x2 plus and so on and so forth a2n xn is equal to b2. So like that I can mentioning am1 x1 plus am2 x2 plus and so on and so forth plus amn xn is equal to b. Yeah. So this can be written as a, it's called a11 a12 so on and so forth a1n, a21 a22 so on and so forth a2n, so on and so forth am1 am2 so on and so forth amn into x1 x2 x3. See that how many elements are there in a single row? There are n elements, so I should have n elements over there because the matrix multiplication is m cross n, and this should be of n cross 1. Then the resulting will be a b1 b2 so on and so forth b m only. So because this n and this n answer is so m cross 1. So this is the system of linear equation in the matrix form. We call it as ax is equal to b. Okay. Now here we are talking about the solution process, where we are talking about the solution of this one. Then further we are going to have an augmented matrix A colon B. I call it as A colon B, or we write it as A slash B, whatever it is. It is not A by B. It is not A by B. It is a separation line. This is called a separation line. It's called separation line. Okay, just in order to distinguish. So we write, we apply the row operations. We apply the operations, row operations preferably. We apply the row operations. We don't apply the column operations. So we apply the row operations. We'll convert into the row echelon form. So the row echelon form is applied. Row echelon form is obtained. In this one, from the row echelon form, we can identify the rank. So you identify the rank of A is equal to R. Then the rank of augmented matrix can be anything. So let us say this is a, I can write a yes or yes. Then we have three issues. If the rank of A is not equal to the rank of augmented matrix, we say that the system has no solution. The system has no solution. or the system is said to be inconsistent. This also is said to be inconsistent. Inconsistent. The other way, okay? The other way, the rank of A is equal to the rank of A augmented matrix. We say that yes, the system is consistent. When I say it's a consistent, there exists a, that is, there exists a solution. There exists a solution. Then that solution can be if the rank of A is equal to the rank of augmented matrix, if it is equal to the number of unknowns, and comparing the value with the number of unknowns, then there exists a unique solution. There exists a unique solution. If the rank of A is equal to the rank of augmented matrix, which is less than the number of unknowns, if it is less than the number of unknowns, we call there exists a, why this is coming, I don't know. Then there exists a infinitely many solutions. Many solutions. So this is the thing to be remember for this case. So this slide is very important because it can cover all the issues related to the system of linear equations. Okay? Okay? So I'll share these notes today because it covers almost the first unit. Okay? Next. So for that case, and again, in the case of, as a special case of the system of linear equations, so a special case is that a homogeneous system of linear equations is a system of linear equations. Okay? So which I can write AX is equal to B. So there the B is taken to be the O. O in the sense it is the right hand side constant matrix is 0. Then this is becoming as AX equal to 0. Now in this case the augmented matrix construction A colon B will be always equal to the A colon O. Now because the last column is a 0 column, it will not affect the rank of augmented matrix. So here the rank of A equal to always the rank of A colon 0. It is always true. That means the system which is the given system. The system is always consistent. Consistent. What do you mean consistent? Consistent in the sense the system has a solution. So it will always have a solution. Now the question is it equal to n or is it less than n? So that is called number of unknowns. Number of unknowns. If it is equal to number of unknowns, there exists a unique solution. There exists a unique solution. So what is that unique solution? That is a 0, 0, 0 solution. If it is less than n, then number of unknowns. Then there exists a non-zero solution. A non-zero solution exists. There exists a non-zero solution. So this is possible when there exists a non-zero solution when rank is less than n, and when rank is 0, this is a unique solution which is always a 0 solution. So this is a special case of the homogeneous system. For a system of linear equation, the homogeneous is a special case because the right hand side is taken to be 0 all the time. So for example, 2x plus 3y is equal to 0, 4x plus 7y is equal to 0, and 3x plus 11y is equal to 0. For the system, always x equal to 0 and y equal to 0 is always a solution. But other than that, when do we have any other solution that is based upon the rank? So what is our number of unknowns? The number of unknowns are 2 here in this case. If the rank is less than 2, then there exists a infinitely many solutions. Otherwise, there is a unique solution. So let me give the problem. What is the problem count? I've forgotten. P14 is the last case. So now P15. P15. Yeah, P15. Let me go with the P15. Show the system are inconsistent. Show that the system is inconsistent. Inconsistent. What is my inconsistent? I need to show that the rank of A is not equal to the rank of augmented matrix. So the system is x plus y plus z is equal to x plus y plus z is equal to 4, 2x plus 5y, 2x plus 5y minus 2z is equal to 3, x plus 7y minus 7z is equal to 5. So the hint is you need to show that the rank of A is not equal to the rank of augmented matrix. P16. Solve the system of equations. Solve. When I ask you to solve, you need to solve whether it is consistent or inconsistent. If it is inconsistent, there is no solution. If it is consistent, you need to solve it. You need to work it. Okay. X plus y plus z is equal to 9. 2x plus 5y plus 7z is equal to 52. 2x plus y plus z is equal to 0. P17. I think this problem we worked out. Let me write down. You can practice it because it comes with a very important issue. X plus 2y plus 3z is equal to 10, and x plus 2y plus lambda z is equal to mu. So for this case, find lambda and mu such that the first case the system has no solution. The system has unique solution. The system has infinitely many solutions. So similar to this, I can give another problem, P18. X plus y plus z is equal to 6. Sorry, x plus y plus 4z is equal to 6. X plus 2y minus 2z is equal to 6. Lambda x plus y plus z is equal to 6. Determine the lambda such that it is consistent. Okay, determine the lambda such that it is consistent or maybe inconsistent. So discuss about the lambda. Okay, and the other way, P19. So it will be like minus 2x plus y plus z is equal to a. X minus 2y plus z is equal to b, and x plus y minus 2z is equal to c. Show that if a plus b plus c is equal to 0, show that if a plus b plus c is equal to 0, the system, if this is the case, the system has no solution. It is not number of solution, it has no solution. Okay, and if a plus b plus c is, I think this is first not equal to 0, the second one is 0, then the system has infinitely many solutions. So this is what you need to, I think it is visible. Let me check it. Yeah, solve means finding a, yes, solving means finding the solution. Okay. I think this is enough for this. If you want, I can give 10 more problems. I can construct new problems. But okay, the thing is that you need to practice the things. That's all. Okay. P19. Let me take P20. This is the problem giving x1 plus x2 plus x3 plus x4 is equal to 0. x1 plus x2 plus x3 minus x4 is equal to 6. Sorry, is 4. No, if I take 6, it will be another problem. x1 plus x2 minus x3 plus x4 is equal to minus 4. x1 minus x2 plus x3 plus x4 is equal to 2. Find whether the following set of equations are consistent. Check whether the system is consistent or not. If it is consistent, find the solution. Otherwise, leave it. It is inconsistent. Okay? P21. 2x plus 3y plus 5z is equal to 9. 7x plus 3y plus 2z is equal to 8. 2x plus 3y plus pz is equal to q. Discuss the nature of the system. For p and q values. So that means you state for what values of p and q the system is inconsistent and the system is consistent, when the system has a solution, when the system has no solution, when it has a unique solution, when this has a infinitely many solutions. This is clear? P22. Because under this category you can expect the questions. So that's why I'm giving more problems for practice. But if I really feel making the things which are already we are familiar, so x plus y plus z is equal to 3, x plus 2y plus 2z is equal to 6, x plus 9y plus az is equal to b. This is not 9z, this is az. This is az is equal to b. Okay, for what values of a and b the system have, for what values of a and b the system has no solution, the system has unique solution, the system has infinitely many solutions. This is clear? Now, after this, I think the time is 12:56. So let me go for 5 more minutes. So the next topic is the concept of eigenvalues and eigenvectors. Okay? Sir, are these important questions for the mid? No. I don't say that you can expect the questions from this. These are the problems that I am giving for the practice purpose. On the same line, you can expect the questions, right? So the concept of eigenvalues and eigenvectors. Now, if A is a given matrix of order n, please remember it should be of order n because I need to evaluate its determinant. So we define the lambda is said to be an eigenvalue, is also called characteristic root. Is also called characteristic root. Okay, it's called eigenvalue if is called eigenvalue if it is a root of characteristic equation given by a minus lambda I equal to 0. So you solve this equation. So that means a is replaced with in the principal diagonal elements. A11 is replaced with minus and 0, 0, 0. 0, A22 minus lambda and 0, 0, 0. So like that 0, 0 and n minus lambda. So this determinant is equated to 0. Expand it. That is an equation which is a nth degree equation. Nth degree equation in lambda. Solve for that, we get n roots. So these roots may be real, all distinct, or may be real. Few may be repeating, and few may be complex numbers. Few may be complex, few may be real. When it is leading to complex, it is out of the syllabus, but still we can proceed in the similar way. Okay. So at lambda equal to lambda 1, lambda 2, lambda 3, there are lambda n, there are n roots. We call them as characteristic roots or eigenvalues. We call them as characteristic roots or eigenvalues. Now we define the eigenvector. So whenever we are defining the eigenvector, it is related to, so eigenvector corresponding to the eigenvalue. So we fix the eigenvalue corresponding to that, we can get the eigenvector. So we say that x is a non-zero vector corresponding to the eigenvalue lambda. So what is this eigenvalue? This eigenvalue of a matrix A, because for a matrix A I can get the eigenvalue. Corresponding to this eigenvalue I can get the x, such that Ax is equal to lambda x. That is the beauty of this. Okay, Ax is equal to lambda x. Once I am going to trying to solve for the different lambdas, so once I say Ax is equal to lambda x, I can rearrange that Ax minus lambda x is equal to 0. Now this can be written as A minus lambda is not possible into x equal to 0, because lambda is a single value. I cannot subtract from a matrix, so I need a help of I. So lambda is multiplied with I. Now it becomes the same order. The minus can be evaluated. Now it is a system of homogeneous equations. Now this is always consistent. Now we are trying to get x is non-zero. When I am talking about x is non-zero, the rank of this, I call it as a B. Let us say this is a matrix B. This is looking like a B. Now the rank of B this rank of B, it should be less than the number of unknowns, less than the number of unknowns. Because of the reason, I should get a non-zero vector. Because if it is equal to n, if it is equal to number of unknowns, there exists a unique solution, it should be a zero solution. But I am talking about a non-zero solution, so certainly the rank will be less than the n. Then the vector which satisfies this equation is called the eigenvector. So we will be talking about if lambda is happening some lambda 1, lambda 2, lambda 3. So if lambda is equal to lambda 1, lambda 2, lambda 3, lambda 4, and so on and so forth, lambda n. For example, these three are same. These three are same. If these three are same, so I say that the lambda is repeated 3 number of times. So we'll be defining the two important properties we call it as geometric multiplicity. We call it as GM, not general manager, GM of lambda. And algebraic multiplicity, we call it as AM. So AM of lambda equal to lambda 1. Suppose this is repeated 3 times. Let us say here these 3 are. So I say that the geometric multiplicity is 3. Now when the lambda is repeated, I am substituting lambda there. The number of linearly independent, I call it as linearly independent. The linearly independent eigenvectors corresponding to lambda. So the number of linearly independent vectors corresponding to lambda is called the algebraic multiplicity. And one important property that the algebraic multiplicity of this lambda equal to lambda 1 will always be less than or equal to the geometric multiplicity of lambda. This is always true. It will not exceed. This is clear? So for this, so the way you know how to solve the system of linear equations, in the similar way I need to find out the solution which is a non-zero solution of the homogeneous part for a given eigenvalue. Okay? So that is our next part. So homogeneous or non-homogeneous makes no much difference. The process is simple. Only the difference is that always the homogeneous system will have a solution, right? It will have a solution. So let me go with the find the, I think what is the problem? Problem number. Can you give the problem number? The problem number is P22 is completed. P23 is find eigenvalues and corresponding eigenvectors of A is equal to, I am giving the A matrix. The matrix A is given -2, 2, -3, 2, 1, 6, 2, 1, -6, -1, -2, 0. I hope this problem we worked out, but let it be. P24 1, 2, -1, 1, 2, -1, 0, 2, 2, 0, 0, 2. I think this also we worked out. P25, P20. I'm trying to give all possibilities with repetition case, with no repetition. Like that I'm trying to select the problems, okay? P26. 6 minus 2, 2. Minus 2, 3 minus 1. 2 minus 1, 3. P27. P27. I think the roots which are coming as 0, 3, 15 we worked out. You already worked out. Yes. Now the roots are 3 minus 1, 1. Minus 1, 5, 1. And 1 minus 1, 3. 1 minus 1, 3. Okay. And take the last problem in this category. Take the last problem in this category. Yes. This is P28, 322, 322, 122, minus 1, minus 1, 0. I think that it's lunchtime. It is already started. Okay. Yes, yes. I'll wind up in 1 minute. Okay. Only one more problem is left. And followed by some properties of eigenvalues and eigenvectors. So I think we have about 15 to 18 properties are there. Okay. Then followed by a diagonalization. So these are the things to be discussed. If time permits, I'll make a note of this. Okay. So with this, I really thank you people for giving the opportunity to review the things, because continuation of 2 hours is very tedious job for you people to listen. Okay. For me, I can take from morning to evening continuously. Yeah, that is not a big problem, right? Take next period also. That's good. Thank you. I'll try because the people, the other faculty members also are in need of the classes to finish the syllabus. So with this, I'll conclude and thank you. Let me take the attendance. I'll stop the issue. I need participants. Yeah, it is 93 members are present, seems to be. So what you do, you can have your lunch. In the meanwhile, I'll collect the attendance. Okay, you need not to respond. I will note down from the list of the people. Okay, now you can carry on for the lunch. Don't log out. Okay, don't log out. I will collect the attendance. In the meanwhile, you can have the lunch. No issue. And thank you. Bye. Thank you. Yeah, thank you. So I will note down the attendance. So roll number 1, 2, 12, 2, 3, 4, 5. Roll number 22 is absent. Thirty is absent. 36 is absent. 44 is absent. 60 is absent. Eight is absent. $78 is